Again, I'd been debating as to what to talk on, okay? And after much thinking, finally I zeroed on. Overall, my theme is going to be probability statistics and finance, this connect, and various topics in that connection. And all this is also related to the theme of the workshop, uncertainty, quantification, etc. Because finance is a domain in which the uncertainty is kind of different. Its uncertainty is arising not because of some act of God or this or that, but it is action of other people. And it's because inability to read other people's mind. If somebody could read everyone else's mind, then the uncertainty would go. He or she, you can figure out whether the stock is going to go up or go down. Okay. Indeed, just the previous talk at the end, this question about coin toss and uncertainty. Okay. My take is slightly different. My take is, really speaking, coin toss is not a random experiment. It's a physical experiment, and if only we could write down all the parameters and write down the complex equation, it's a physical phenomena, and the trajectory is deterministic provided you can measure all the relevant parameters accurately. Okay. So what we call randomness there is our inability to measure all the required parameters, and because of that, the uncertainty that is arising in the whether it will be head or tail. It is nothing intrinsically random about it, in my view. Okay? And in fact, most examples of what we study in textbooks of randomness generally come from this category. The uncertainty is arising out of various reasons. One could be simply it is an event in future. So there is uncertainty. I mean, the other thing could be inability. If I ask everyone a question, give answer yes or no, distribute slips, and everybody answers yes or no, without looking at the slips, I can't. There is uncertainty for me. How many yes, how many no? It's not really a random event because everybody knows exactly what their views are and they have been recorded in a box. So it is my inability to read everybody's mind. So in a lot of situations, the uncertainty, in my view, is of this kind, and of course, then the notion of randomness and associated probabilities are mathematical concepts, and you might wonder what would mathematics do if you don't know what it is. Okay. So there are many examples where it has been found useful. I'm not going to go over that because that itself could be a whole lecture on that theme, but so I would just sum up by saying that my view is that randomness is in the eye of the observer. The observer may not know certain things, and that's why the outcome is uncertain. Okay. For example, if I toss a coin, and if those in the front bench can see it and those in the back cannot see it, your information set is different. Okay, and let's say they can only partially see it, not quite exactly, but it appears that perhaps it's a tail, perhaps. So their model could be different, though random, their model could be different from yours. Okay. So in finance too, you have to incorporate all the information that you have and put that in and then create a reasonable model. Okay. And of course, last 20 years, 25 years, this interplay is very strong, maths and finance, or when they say math and finance, the root is through probability statistics, that you remember. There is very little connect between math and finance if you delete the root via probability statistics. Okay. Now, so I am going to generally speak on this theme, and so Let us start with the Gaussian distribution, and I suppose most participants here are either done masters in statistics or are doing, and they would know what is normal distribution, Gaussian distribution. But I am going over the history. It's always good to revisit history. You see, it was introduced by Gauss in his work Theory of Errors in 1809. It's about 100 years before key statistical concepts were born, about 100, at least 90 years before. So well before that. Okay, we could trace this as almost the beginning of modern thought of statistics. And the Gaussian distribution later came to be known as normal distribution, at least when I was a student, and by then, and I suppose you would have learned it also, as a normal distribution, and it has a central place in statistics. Apart from some examples of other distribution, most of the theory as we study in BSc, MSc statistics courses is related with normal distribution. There is a reason for that. One of the reasons was that it was found that data from various natural phenomena followed Gaussian or normal distribution. Okay. The central limit theorem, which again goes back to 1810, the Laplace version of this, De Moivre-Laplace version. So the central limit theorem and its generalizations that follow gave a theoretical justification for omnipresence of the Gaussian distribution. So more or less the message was that, on any phenomena you make repeated measurements independently and you aggregate them, what you are going to see is normal distribution. Okay. That is what, in loose terms, is the content of central limit theorem, and perhaps used to explain why you go to a college campus and take the data on heights of individuals, you take data on weights of students. If you come to CMI, which has only 100 population, you may not see normal distribution. I don't know how many students are there at ISER.
I don't know the exact number.
In 1,000 or 2,000, 5,000? And if you go to Calcutta University, then of course it is 50,000 and more. The lower bound is 50,000, I suppose.
Including the colleges.
So, once the number is large, if you take data on this characteristics I am calling height or weight, you are going to see normal distribution. Now we can, without even doing that, I can say that, and earlier people did these experiments and saw that it fits normal, etc., etc. Same is the case when measurements are made by different people on the same physical phenomena, or on a physical phenomena, repeated measurements are done across days. Various such experiments people did and found that normal distribution seems to describe the uncertainty behind whatever you are observing rather well. Okay. Here is an interesting bit. I have actually got the exact quote. So apparently Carl Pearson is the one who named it normal distribution. And in italics is a quote by Carl Pearson written in 1920. Many years ago, I called the Laplace Gaussian curve the normal curve. So he calls it Laplace Gaussian. He doesn't call it Gaussian first. Laplace Gaussian curve, the normal curve, which name, while it avoids an international question of priority. So perhaps among the French and Norwegians, maybe there was a question about whether it should be Laplace or Gaussian and so on and so forth. So that's why he's calling international question of priority. It has the disadvantage of leading people to believe that all other distributions of frequency are in one sense or another abnormal. Okay. So without saying in as many words, the use of the word normal conveys that last sentence. I mean, as a student I believed that, and I suppose at least some of you would have believed that. No teacher would have told you this phrase, but you kind of, over a period of time, that is what our thinking leads us to. Okay? And Carl Pearson wrote that it is unfortunate that he is responsible for this. Okay. In fact, much after it was introduced, it was found that normal distribution is extremely amenable to mathematical treatment, and explicit formulae for moments are available, easy to generalize to multi-dimensions, and whole lot of other mathematical derivations, some of which we would have studied in courses and many more which we have not studied but are there in the literature, starting with characterizations, starting with distributions of various associated quantities, exact derivations. Okay. So, so on one hand it was occurring in large number of examples, on the other hand it was very amenable to mathematical treatment and therefore it became extremely popular, central place in probability statistics for years to come. Also, another very important point, that it is completely determined by very few parameters. Indeed, multidimensional case means, variances and correlations. So if you come up with a very precise model but which has thousands of parameters, then it is not very good, because when you estimate these parameters you really don't know how small errors in each of them will translate to your final model. Okay? So sensitive analysis, which is there in the theme of this workshop. Okay? So not negation of sensitive is robust, and generally in applications one prefers a very robust model. Okay. So in that sense normal is very nice because it has very small number of parameters. Okay. I must mention this classical book. I am not sure whether later generation students study this or not, are even aware of this or not, but if not, I would recommend at least go to the library and take a look. This is, at least all libraries in India certainly will have this, Linear Statistical Inference by C.R. Rao. The book has many things going for it, but particularly I am talking now is when normal distribution is introduced, Dr. Rao has gone at length in describing several situations from real life, making what appears like very natural looking assumptions or hypotheses, and just from there deriving that the uncertainty quantification must be via normal curve. Okay. It could be people firing a bullet at a target. Okay. That is one thing I remember, and there are many more like that. Okay. And very interesting. This book itself is interesting, but just to see that how very simple descriptions of a phenomena can lead you to a complete description of the uncertainty. Okay. So as I said, most of the statistical theory was centered around normal distribution. And certainly my generation and senior to me, and I'm sure those who are a couple of decades younger to me at least, grew up believing that once one has a large number of observations, the data must follow normal. And large I have put in bold because our book said n equal to 30 is large. Okay. So, let me briefly talk about the multivariate normal. Indeed, in our coursework we see several examples of univariate distributions, uniform, exponential, and many more. Okay. Of course, chi-square, TF, which are in relation with analysis with normal distribution, and several others. And there is even handbook of distributions, a fat book compiled by people. Large number of univariate models are available, discrete as well as continuous. However, if you have had a course in multivariate statistics, and if you have not, you go and look at the course content at various universities of multivariate statistics, course title multivariate statistics or multivariate statistical analysis or any name similar to this. And if you read the contents, it amounts to a course on multivariate normal distribution, because almost everything done in the course relates to multivariate normal distribution. There may be something related to Wishart distribution, which is a multivariate distribution, but it occurs only because it is arising as, if you have sample from multivariate normal, you estimate variance covariance matrix, its distribution is Wishart. Okay. So the entire focus of multivariate statistics course invariably is multivariate normal. Okay. Nothing wrong with it if most data seem to follow it and it is amenable to mathematical treatment, nothing wrong with it. All right. A few slides on going beyond just multivariate in discrete. When you have talking about observations in the continuum, then it has an analog in infinite dimension, which is called Gaussian process. Interestingly, here the word normal process was never used. So I never knew the name of normal distribution as Gaussian distribution because no book described it that way. But when we went to infinite dimension, it says Gaussian process. So this has been used with great success in various problems, including signal detection, filtering theory, control theory, where the noise in transmission is modeled as a Brownian motion. So in interplay of probability theory and engineering, particularly electrical engineering and communication sciences, that was one of the very early success stories where using probabilistic techniques and probabilistic models, they derived various conclusions which were put in practice, put in an instrument, and people without knowing are using as instruments which have these things built in. In fact, in one context I had read even a statement which is perhaps exaggerated, but it at least has a grain of truth in that if it were not for developments in signal detection, filtering and control, what was called the Apollo mission those days, the mission to moon and the satellites, etc., that would not have been possible. Because when they launch a satellite, you have a certain information, and based on that you decide on a trajectory and control and you path, and you fire the missile, fire the satellite with that settings. But even a minuscule deviation in the actual trajectory and your planned trajectory, when you are traveling such a large distance, it can go haywire, and they realize that if they can control within, say, 1/100th of a radian in firing, 1/100th of a radian can translate to going to the moon or passing several 100,000 miles away from the moon, right? So they needed to continuously track it and then apply corrections and then make the trajectory go. So in all this, and all communications are subject to noise, remember, on electrical signals. So these days, most of you from using internet at home, you may have broadband, etc., and you are not using anymore a dial-up connection. But if you just go to, maybe in your childhood you might have seen your parents using a dial-up connection, or I certainly remember. And there was always this question that if you make a phone call on your landline, you will see a lot of static behind, a lot of noise in the background. And yet when you use the same connect for dial-up and connect to the internet, you don't see, you don't get garbled messages. Either the connection snaps or you get a perfect message. So all kinds of error detecting codes as well as error correction mechanisms are built into these devices. Okay. All right. So using Gaussian process as a model for noise, as in Brownian motion, was one of the big success stories in interplay between mathematics or probability theory on one hand and electrical engineering on the other. Okay, so now I come to my theme, namely finance. And here again, the history is very interesting. When I as a student studied Brownian motion, all books would say 1905 Einstein used Brownian motion in his work on kinetic theory of gases. Okay. So whereas the macro equation was a deterministic heat equation or described by Einstein, the microscopic picture corresponded to that of a Brownian motion. Not much was written by Einstein about Brownian motion, but it is very much there. However, 5 years earlier, Becquerel had used Brownian motion to model stock prices in first ever attempt at option pricing theory in a PhD thesis done in France, in Paris. In fact, the books that I studied simply said Becquerel had also considered it earlier, would not even say in what context. This work of Becquerel did not get much attention from the finance world because under this model, the stock prices could also be negative. It has a normal distribution. Once you have a normal distribution, however large may be your mean and standard deviation may be small, but there is a positive probability that it has a negative value. And perhaps this was a reason, or otherwise this work was completely ignored by the finance world. And it is even said that Becquerel may have not even got his PhD, but for the fact that his advisor was the big dad of maths in France at that time, Henri Poincaré himself. So nobody could deny him a PhD thesis, but even Henri Poincaré's influence did not get him a regular faculty position. And he had to move from one place to the other and so on and so forth. In this sense, connect between math and finance, a formal connect between math and finance, and certainly Brownian motion and any applied work goes to finance before the connect with physics. Before that, Brown, after whom it is named, was a botanist, and he had written down a phrase which said that, about observing if you have pollen particles in a glass of water, they don't seem to be static, they seem to be moving all around, and he had described that motion in English. And what he described in English is later turned out to be a characterization on Brownian motion. So those who are interested, they should go and on the internet search how Brown described the motion of pollen particles suspended in water, and how it characterized. So how simple looking descriptions can actually characterize a whole uncertainty quantification. So now modern generation, you would have heard that in 1973 Black and Scholes modeled logarithm of stock price as a Brownian motion, which is also described as a model as geometric Brownian motion. And using this model, they derived a pricing formula for European call options. This became big news because Scholes, along with Merton, got Nobel Prize for this work. Black was no more by the time the Nobel Prize was awarded. In fact, about 25 years earlier to Black and Scholes, Markowitz had modeled daily stock returns in a portfolio. Now it is not just one stock, but a portfolio of stock, which means several stocks together. He modeled this portfolio as a multivariate normal distribution. Okay? And then he derived optimal portfolio selection that yields best what is called risk-return trade-off. More on this we will see later. And since he was modeling it as a normal distribution, in the Gaussian world, the variance is seen as a proxy for risk or as a measurement for risk. Higher the for the same return, higher the standard deviation, more is the risk. If smaller is the standard deviation, less is risk. Okay. So Markowitz had argued that you either fix the quantum of risk you are willing to handle and then maximize the return, or you set a target for your return and then minimize the risk, as in minimize the standard deviation. And thereby had developed a theory which again is interesting. This was a PhD thesis, and in US, PhD thesis is generally examined internally in the university, and it is your advisor and two other members. And one of the members, another leading economist, was unwilling to sign on the thesis, saying this all looks like mathematics, where is economics in this? Okay. Grudgingly he signed off on this PhD thesis. Of course, Markowitz himself got a Nobel Prize for this work some years later in economics. Of course, there is no Nobel Prize in maths or statistics or probability, so it has to be in economics. So what this is saying is something which appears to be at that point of time, what are you doing? Nobody is impressed by the work, may later become very, very important. Okay. So, so I made a digression to multivariate models and processes and so on. Let us come back to univariate models. Okay. As we talked, it was believed that most data one would encounter in real life would be normal, corroborated by data obtained from diverse domains, physical observations on some phenomena, agriculture data. Agriculture was one big application area of statistics with great success. As you know, there is an institution in India called ISRI, which is Agricultural Statistics Research Institute. So it was strong enough to have a separate institute for this purpose, because importance of agriculture, at least for India, generally for mankind, and in particular for India, cannot be overstressed. And a lot of improvements in agricultural output and production, etc., due to various other factors, but statistics has played a key role in that. Lots of statistical ideas have gone in. Again, intrinsically normal distribution. Okay. Anthropometric data. So, Dr. Rao's book has lots of examples of, you make various measurements to classify whether a skull belongs to this race or that race, etc. There again, one sees normal distribution. Weather data. So, rainfall prediction and weather, it is another very big area of uncertainty and a lot of debate in public, and still a lot of work to be done. If one could improve even 5% the rainfall prediction models, short term specifically, not so much long term, there is not much hope, but short term, it can yield large dividends, because it can tell farmers when to start sowing, when to do various activities related with agriculture, provided they can predict weather better. Okay. So, all right. Perhaps the first departure of from normality of not just one data set, but one kind of phenomena where repeatedly different people collect data and each one comes up with something is wrong here, it is not normal. If your belief is that everything is normal, the only thing you will conclude is something is wrong about whatever you are doing. But repeatedly different people measuring so, showing that this was data on income. So, you take a country or a province or something and you collect data on incomes of individuals. Of course, that doesn't show normality, but you will say, okay, that is all positive variables. So people thought, okay, let's take log transformation on the logarithm scale, it should come close to normal. It comes closer to normal, but still doesn't fit quite. And that is where this distribution called Pareto distribution came into picture. And this becomes a very important point in a course on econometrics. Okay? That you have to go beyond normal distribution, start looking at what is Pareto and so on and so forth. So, there can be many intrinsic reasons as to why this happens, but in general, more or less now it is known that you take data on anything from economics, finance domain, and often you don't see normality. Okay? And one explanation I have, or one thing which separates this economic domain with the other domains, the natural sciences, and this is behavioral science, is in natural science there is no feedback loop. Whatever you believe in, nature will keep doing whatever it is. Instead of normal, you believe it is a fat tail distribution, people's height will remain the same. And so goes for agricultural production. Whatever you believe doesn't matter. Nature will keep doing its job. It is neither trying to help you nor try to stop you. It's neither a cooperative game or it is not a zero-sum game. Okay. Whereas when you come to economic domain, the equations change. Collectively, if everybody believes something, that will happen. If everybody believes that ICICI Bank is going to go bankrupt, everybody rushes to withdraw their money, and no bank, not just ICICI, I just picked up ICICI for no bank actually has a reserves to settle all their depositors on a given day. No bank, because if they do, then they cannot be running a bank and they cannot be in the business. Okay. So this is one example where there is a very strong feedback loop. Okay. And perhaps this is so for all economic domain data, and perhaps that might explain why we see departure from normality when you see data from economic domain. Okay. Why I picked ICICI was about maybe about 10 to 15 years ago, or 10 years ago, there was suddenly a rumor in Bombay that ICICI Bank is going bankrupt and all its ATMs are running dry. It is well before demonetization. People had not seen ATM machines go dry in the large scale that happened 2 years ago. Okay, this is well before that, and this was spreading like fire, and everybody was running. And naturally, if everybody rushes to their neighborhood ICICI ATM, the ATM will run dry of money. It was a weekend, and the strong monitoring of this activity, that how much withdrawal is happening, are repeated requests being denied because of want of cash, etc., etc. So someone in ICICI Central Control found this out and alerted higher management, and they got into an action. And over the weekend, they ensured that enough vans were there going all around, continuously stacking up more cash in ICICI ATMs till the rumors died and everything returned to normal. Okay, so this business about feedback loop affecting the output, one has to keep in mind. And same goes with, I talked about ATM, but same goes about stock market. If there is a rumor that such and such stock is going to tank, this company is going to go bankrupt, its stock price will nosedive. Because everybody who holds those shares is going to go and try to sell it off in the market. Okay. So any large movement of positive or negative has a feedback effect. Large positive, namely large number of people trying to buy, the prices will go up much more than the usual expected, and large number of people wanting to sell, it will go down much more than expected, disturbing the normal model. Okay. So for the income also, it was found that if you try to fit the data and try to, now modern days you can use R and try to do the QQ plot with normal, what you will see that at the center it is quite straight, that means the fit is very good in the center, and what goes wrong is at the two ends. Instead of looking at straight line, they look like wiggly creatures dropping down or going up like that. Okay. So the fit, so the two ends are what are called tails of the distribution and the middle. So the fit was very good in the middle, in the tails it is off. Now, earlier I had not talked about exactly what is it that Markowitz and Black-Scholes were modeling. Now here is a concrete equation. What they were modeling what is called daily stock return. So if Sn is the price of a stock or the share on the nth day, okay, they are modeling Sn minus 1 divided by Sn minus 1, or roughly speaking, when this is small, this is roughly equal to when you do this increment log Sn minus log Sn minus 1. So either returns on the log scale or return stock like this. So Markowitz Black-Scholes models can be read to mean that these quantities are normally distributed and independent across days, okay, for as n changes. And if you are having a univariate stock, then just univariate normal, and Markowitz was primarily discussing multivariate. So each component you compute the return, thereby you can compute a vector of returns, and you call that vector of returns as having a multivariate normal distribution. Okay. However, it has been seen by many people who have done such empirical studies that most of the time the returns from the stock market do not follow normal distribution. And this is, people have studied data from different markets over different time periods, okay, and departure from normality has been observed. So I'm going to present you some R analysis on the next slide. So I've taken data for about 2 years, 2015 and 16, and from New York Stock Exchange, taking the stocks that appear in S&P 500 index. Okay, I could get the complete data on 496 out of this. There were some incomplete NAs in that file, so I've deleted those. So 496, and I'm going to show you results on this. Now, it is important whenever you see any data done by your professor, any conference, etc., to know how the data was taken. Is it that out of these 5, I can always take some 10 stocks, okay, actual stocks, 10, and whatever story I want to tell you, I can show you that these 10 corroborate that story. Okay. So you have to know that it should not have been handpicked by me to just say that whatever I am saying is better than whatever else others are saying. It is very important. So here it is important that I have not handpicked the stocks. S&P stands for Standard and Poor. It is like our Sensex or Nifty, which are the indices on the Indian stock market. Standards and Poor, S&P is one of the major indices on the New York Stock Exchange, and S&P 500 are all very prestigious companies, very profitable and heavily traded. That's the other part, that there are some companies where there is no trade happening. Then we can't really interpret much about, if one trade happens today, another happens 5 days later, etc., we can't interpret much probabilistically. So stock market data, one has to take what are called active stocks. What is an active stock? Active stock is stocks for which large number of buy and sell are happening. Okay. All right. So so what I have done is I have taken this 496 stocks data for about 520 days in period around 2015-16. Exact dates I don't remember. And the next screen shows the result of applying the Shapiro-Wilks test for normality on this data. So let's say IBM. So I will have one series of prices of IBM, right? Then I compute their daily return by this formula. Sn plus 1, Sn minus 1 divided by Sn minus 1. Okay. So I will have 525 values of, or 526, I have data on 527 days, so I will have 526 values of this Sn minus 1 by Sn minus 1. Okay. Now these 526, if the hypothesis that Markowitz and or Black-Scholes had, that these are IID observations from a normal distribution, if that were true, then this 526 observed values should fit a normal distribution. Okay, and okay, so here is the output screen from R. As you can see that I have some data which I have called returns NA because I removed the NA fields, NA series, and then for each data series I apply the Shapiro-Wilks test, and I store the p-value. And if I display this 496 p-values, it is very difficult to comprehend. So what I have done, so this nice command, it says how many of these the p-value is above this. So less than or whatever. So at least for 90 out of the 496, the normality assumption is highly rejected very strongly. That the chances, I think there is a sign mistake I have done somewhere, but for most of them, the somewhere my interpretation has gone wrong here. But for the output of the R thing was that for most of the stocks, the normality is rejected very strongly. and not even a single one passes normality at 1%. Okay? These are the ones which pass at 1%, these are the ones which pass at 0.1%, these are the ones which pass at 0.001%, etc. Okay? So, for most of them, the hypothesis of normality is rejected very, very strongly. And now the interesting thing is, what I have shown just now is for 2015-16 data, but people have observed it from going back in time, 60s and 50s already. That you take actual data and apply normality test to the actual data, and you are going to see departure from normality. So this has been known. On the other hand, the Black-Scholes framework for modeling stock returns via Brownian motion or geometric Brownian motion and the option pricing theory, etc., they became center stage of this piece of work, and applications also, not just in theory but applications. After the Black-Scholes thing became center stage, whole lot of people who are mathematically trained or physics graduates have been working on Wall Street day in and day out, computing various parameters involved with Black-Scholes models, and the entities which are doing trading is using them. Not that they exactly believe in Black-Scholes model, but they know it is approximate reality, so they take that input and then modify it suitably. But so here is one interesting question, that while people knew that this is a very bad model, because it was only the model for which they could do concrete mathematics and get closed form answers, people have been using that. Okay? There have been critiques of that, several, but it still continues to be the center stage. I'll just mention one such critique. How many of you have heard the name Mandelbrot and fractals? Okay. So younger generation doesn't seem to have heard about fractals, but these are interesting objects, and maybe about 25 years ago there were discussion all over in the mathematical world about it. It so happened at that time I was in Santa Barbara, and with a colleague there we were trying to do option pricing for models deviating from Black-Scholes with fat tail distributions, which were more realistic. Didn't get much anywhere, but we were trying to do. At that time, we saw that Mandelbrot was going to visit Santa Barbara, and going to give a talk on, like a big public talk with thousands of people, big auditorium on fractals. So my co-author, Rache, who was on the faculty at Santa Barbara, he said, let's go and meet Mandelbrot, because Mandelbrot had written a paper in 1966, well before Black-Scholes, about modeling of stock prices and why it should be bias stable and so on. So it was a 2-page paper. So I tried to tell Rachev that, see, that is long back. This was 92, he had written in 66. After that, he has become a big man talking about fractals. He won't even remember that 2-page paper, and we will make fool of ourselves if we try to go and meet him. So we agreed on the following. So Rachev said, okay, let me call his office and let me call his hotel and leave a message that so and so would like to meet you to discuss this following. If he responds, good. If he doesn't respond, forgotten. So we leave a message. Next day, I come to the department at 9 o'clock and I see Mandelbrot has already come to the statistics department, leave alone replying to our message. And we had a nice 1.5 hour chat with him, and he seemed to be very exercised about that when you know that it's a bad model, just because you can work the maths of it, you continue to use it, how ridiculous it can be. Okay. But anyway, so the it's till date it is used a lot, and Black-Scholes model, and people suitably apply modifications to whatever output the Black-Scholes model gives. Okay. Now let me come to risk in finance. Okay. the standard deviation of returns has been taken as a measure of risk, and this goes back at least to Markowitz in the late 40s. Several decades later, it was recognized that if underlying distribution is not normal, standard deviation may be underestimating the risk. Okay. Now, let us understand exactly what do they mean by risk. If we say standard deviation measures risk, then what is risk? Okay. So one way to understand risk is the following. It would be unreasonable to expect that in the stock market, the loss has a strict upper bound. If you want a strict upper bound, how much loss you can get, that whole company can go bankrupt and the paper you are having is just like a Raddi paper. It has no value other than to wrap something in that. Okay? If the company goes bankrupt, so therefore, strictly speaking, if you make an investment in stock market, the strict upper bound for the loss is the whole value you have invested. And if that is your assessment, then you can't really be doing anything. Okay? So, what people come up with the following. What one looks for is a bound K so that the loss does not exceed K with say 99% probability. 99 could be 95, it could be 99.9, could be 99.99 depending on whatever your the context is. Okay. For an individual investor, even 95 may be sufficient. For a bank, 99 may not be sufficient. If you have 100 banks and every year one of those 100 banks fails, your economic system will collapse. So what level of for VAR to take would depend on the context. All right. But let's for a discussion say that we take 99%, and this K has been called value at risk. So for an individual investor, what it means is that you decide, okay, you are going to invest so much, you are willing to live with a 10,000 rupee loss. Okay, that much you are willing to accept, or 1 lakh rupees loss. So then you put your value at risk as 1 lakh and try to come up with your investment strategies. All right. You hope that you will gain, that is why you are investing, but in the kind of worst case scenario, this you ignore that with 1% it could be even worse. Okay. Now, so this is what has been called value at risk. Now, if the distribution is normal, then this K can be completely expressed as mu minus 2.38 sigma with a minus sign. So, mu is the return, that is your gain distribution, mean of the gain distribution. If you want to take loss, then it has a minus of gain. That's why this minus sign. And this is the lower 1 percentile point, and then when you take negative, it is the upper 99 percentile point. Okay. So, the mean and sigma completely determine the value at risk for a normal distribution, and now on the next screen, what I am going to show is that for the 496 stocks that we had chosen, I am going to compute the ratio of 99 percentile point of the loss distribution. I should have put not percentage sign but percentile. 99 percentile of the loss distribution, and this quantity which would have been the, if the distribution was normal, then this ratio should be 1. If it is exactly normal, if it is nearly normal, it should be close to 1. Okay. So, so I have just computed this ratio, and for 10 of these, it is less than 0.9. So actually, it is good news. Your sigma estimate of risk is actually more conservative. It is less than 1 in only 10% of the cases. In nearly 95% of the cases or 92% of the cases, it is bigger than 1.05. In 347 out of 495, it is bigger than 1.1. And in 136, it is even bigger than 1.25. So far away from 1. So what this is meaning is that when you are using sigma as measure of risk, you are underestimating the risk by almost 25%. That is what the signal there is saying. And of course, for some of them, it is even bigger than 1.5. So that is showing very strong departure from normality, this is strong departure from normality, and so on and so forth. So what this is saying is that when you deviate from normal distribution, okay, the sigma may not really be a good measure for measuring risk. Okay? And after various banking crises across the world, the bankers from different countries have been getting together and trying to come up with what they call risk management framework. And risk management comes first is risk assessment. So their aim is that the international monetary system should not collapse. In particular, every country should ensure that their own monetary system does not collapse. And what they come up with is that each entity has to keep what they call a fixed reserve. Okay. A bank, it has to estimate how much of offtake on a given day, how many people may come to withdraw money, or how much of cash is required for them to do their daily operations and come to the 99th percentile point for that, and ensure that that much cash is available every day so that they never face cash out situation. Okay. So these are all these are international agreements named after the Basel II Accord or Basel II Accord, and all countries are signatory to that, and these are part of our regulation. So one instance where statistical terms have actually gone into law, the value at risk is a technical term which is part of international regulations including our country. Okay. And what this will say for a bank is that, so much cash reserve they must keep every day. Only the rest. So if they have, let's say 100 crores deposit, and they based on various considerations, if it is determined that the VAR is 5 crores on a daily basis, then they have to retain 5 crores. They can only lend 95 crores to other businesses, and they have to keep 5 crores cash reserve. And if you try to read various things which are happening on the finance domain, the clash between central government and the Reserve Bank and so on and so forth, various things are also related to this, that they want to ease means somehow RBI should reduce this cash requirements, should ease the restrictions on the member banks and so on and so forth. This is just one of the many points in their debate discussion. But when they say risk management, the first thing which comes is risk assessment, and then trying to take steps so that you mitigate the risk and ensure that the risk event doesn't happen. Okay? And using normal distribution was underestimating risk. And that is why internationally the various banks have agreed that their framework should be that they make a realistic assessment of the uncertainty and come up with a VAR rather than sigma as their measure of risk, and accordingly modify their laws. So interestingly, as Dr. Nanda said, there was a period when I worked with the software industry or consulting industry for 4 years. They were in both software business and consulting, and in the process I saw lots of interesting things. So let's say some entity is saying that, they are producing risk management software which is Basel II compliant. Earlier versions had only sigma, now they have made it VAR based. Okay. Okay. Of course, their technical literature is all, written in big language but with no content. And with one such entity, I was able to quiz the person who wrote that. And finally, it appeared that instead of sigma, they were this 2.38 sigma minus mu was the quantity they are displaying as VAR, which is one and the same thing. If you use their sigma version or the VAR version, they will give you the same answer because they are just transforming it. So that apart, the VAR becomes a very important object for risk management. I'm almost coming to the end of the first hour, and this I have already talked about. Now, this will lead up to our next session, so that is why I want to end with this. So for one variable, univariate, we have fat tail distribution models. You have exponential, you can even have Cauchy, you have stable distributions and so on and so forth. but we don't have any appropriate multivariate model. If I ask you to come up with an example where a bivariate distribution, each marginal is uniform and there is a correlation half, your coursework would not have taught you any such model. Okay? And that is what leads to the notion of what is a copula, which will be the topic of my next talk. So, in the absence of multivariate models, what people did mostly was, you use either you use normal model with realistic correlation, use multivariate distribution, normal distribution. Now you know that you are kind of underestimating risk because your tails are not quite what they should be. So, ad hoc factor, you say risk, this model is giving so much risk, multiply it 2 times or 1.5 times, it's ad hoc inflation. Now you say it is a realistic one. So, that was one approach. The other approach was, you ignore correlation, now take marginal distributions fat-tailed, do the analysis and once again resort back to an ad hoc multiplication factor because you have ignored correlations in your analysis. Okay? Here comes the notion of a copula, which we will talk next, but during the break, if you have access to internet, I suggest the following. Do a Google search and type in the search phrase, no phrase, just words, the formula that killed Wall Street, as if people believe that it is all the, and this is related to the 2008 crash on the Lehman Brothers crash and resulting events in the stock market, as if one formula was responsible for this huge disaster which happened across the globe. This morning when I looked, it had so many results. So, we'll come to copula. So, copula is a notion which was there in statistics literature but completely ignored. We were never taught what is a copula. Though this original paper which described copula appeared in a leading journal in 1960s, and I was doing masters at ISI in 78, I did not learn. As a PhD student, I did not learn. In fact, as late as 2000, by when I had been on the faculty at ISI for 16 years and a full professor for several years, I happened to go and do a training program for ICICI recruits on stochastic calculus. And one of the participants who had a BStat at ISI, he said, "Sir, I want to discuss some recent paper with you in the evening." I said, "All right." So he comes to me and starts talking, if you take the copula model, blah, blah, blah. I said, wait, what is a copula model? Now it was his thing to be surprised that here is someone who is a professor of probability at ISI for so many years and he doesn't know what is a copula. So I had to tell him, see, I don't know. So for discussion, you have to tell me what is a copula. So he described and it is then I was a bit worried that is it somehow, how come I missed it? Then what I did, I went back to ISI and whenever I meet some of my teachers, to each of them I asked about copula and none of them had heard of it. So, it was a notion which was there in the literature, stat literature. It came to the forefront because of finance world discovered that. Okay? And apart from that, that formula that killed Wall Street involves copula. So, apart from that spicy story, but there is a real meat in this thing called copula. It allows you to construct realistic multivariate models of uncertainty, even when you do not require normality on the univariate ones. And that is what we will talk in the next session. Let me stop.